we have next speaker called Nishino in Drexel University. He is one of the most energetic researcher in computer vision area. He also received PhD thesis in here, University of Tokyo, and actually the supervisor of PhD thesis is the same as Imari-san. So, so please start your presentation after.
Okay, thanks for the introduction, and thank you to the organizers for bringing me back to this alma mater to talk about my favorite research. So before I start, I wanted to introduce and acknowledge my past and current students who actually did all the work that I'm going to talk about. And today I'm going to highlight the work by Jeff, Steve, and Gabe, mainly sponsored by ONR and NSF. So I live in Philadelphia, and that's where the movie Rocky was shot. And maybe some of you are too young to know that movie, but I believe many of you actually know those famous steps of the museum in Philadelphia that Rocky used to run up every morning. And there's a statue of Rocky at the foot of these steps that tourists love to take pictures with. And in this photograph, it's very easy for you to actually identify which one is Sylvester Stallone, right? But would that be an easy task for computers, right? In computer vision, we have made really tremendous progress in terms of object recognition by mainly relying on this fundamental assumption that shape actually encodes what the object is. For instance, by modeling the way our body parts create edges in the images and how they interconnect. But both of these, the statue and the Sylvester Stallone, have similar shapes which would respond to person detectors. But what really distinguishes Rocky from this fake lifeless statue is really his tan flesh, his worn jeans and silky jacket, and maybe his receding hair, right? So it's really what the shape is made of, the material that needs to be recognized. And ideally, you actually want to tell what the material is without knowing what the object is. Because our belief in the object and the material should go hand in hand to reinforce our understanding about the visual world surrounding us. And in fact, the shape cues that we often rely on can be very misleading. As Carl Werner carefully crafts in his Foodscape series, and if you don't know this, you should definitely Google his name, you might find that your book is made of ham on a table of cheese, on an alley paved with wheat bread, complete with a tree line of broccoli, right? So, but yet in computer vision, we think that shape really dictates our visual world. Just like Broom depicts in this ingenious paintings, we recognize, just like this, but we as human beings actually recognize a bed, not just because it has this boxy shape, but because it has these fluffy pillows on it, silky sheets draped over it, right? So it's about time that we try to grant computers the same ability of visually recognizing materials, okay? And it's really essential to realize material recognition independent of object recognition for the sake of computer vision, because, for instance, think about asking your personal robot that you'll purchase 10 years from now to put a wool glove on your hand in a really cold winter day. The robot will need to tell that one is made of leather, one is made of wool, and one is made of human flesh, despite the fact that they all look like hands, right? So that you can pick the right one up and put it on your hand instead of ripping your hand off and stuffing it in the leather glove. So, but of course, telling the material just from its looks is really challenging. There's no doubt about that. But if you think about it, there has to be some visual information deeply encoded in the images that hints at the materials. As we, as human beings, can easily tell that this Obama is probably not going to respond to our request of a handshake. And if we actually bite into that sushi, we might lose our teeth because it's an iPhone case. And don't ask me why Japanese are so obsessed about sushi. So really the goal is to extract and analyze such untapped visual information hidden in the images that hints at the materials, so that it can help higher level image understanding tasks. So my research for the past several years have been geared towards paving the way to enabling the use of materials as visual context in computer vision and scene understanding. Now, of course, as Ted Adelson really summarizes in this very inspiring paper in 2001, the challenge really lies in the fact that the material appearance is an end result of a combination of a number of factors ranging from the intrinsic mechanics like viscosity to the extrinsic optics like the viewing direction, the illumination direction. And of course, we as human beings can sometimes tell things that even at the deepest level, like around here, for instance, by being able to tell that this is actually a skin cream and cream cheese swirled by the same knife motion. But trying to do that full decomposition with a computer just from a single image, say for instance, is going to be probably a bleak endeavor. But the really good news is that we just have to reveal just enough information that's unique to the material from the images. So today, let me discuss about two distinct approaches. And I believe these have a lot in common with what you guys have been talking about. So please try to draw the parallel there. And one is that tries to recover the intrinsic optics, namely the reflectance that is more or less unique to the material just from the image. The other approach is going to be directly trying to classify each pixel into different materials. Okay, so the first approach is going to be a generative one, or inverse optics, if you will, where we basically try to undo the image formation process so that we can recover the fundamental building blocks of the scene, namely the geometry, reflectance, and illumination. And the hope here is that the reflectance will tell us what the material is. And here, the key is going to be finding a way to represent the variability of real-world reflectance. The second approach is going to be a discriminative one, in which we forego all the physically based analysis of the image and directly try to classify each pixel into different materials. And here the challenge lies in representing the material's large interclass variabilities in its appearance. Okay, so I'm going to talk about these two distinct approaches. So let me start with the generative approach. Now, we are interested in what I call radiometric decomposition, which, as I said, is about inverting the image formation process to estimate the physical roots, namely the material as the reflectance, the geometry like surface normals, and the illumination as, say, for instance, a spherical panorama. And many of the long-standing problems in computer vision can actually be thought of as specific instances of this general radiometric decomposition problem, where in many cases, you try to recover one or two of the three unknowns by assuming that the other one is known. But unfortunately, in most of these works, we make unrealistically simplistic assumptions like the reflectance being Lambertian, or a little bit more sophisticated model would be Lambertian plus Torrance spiral, right? And that's it. Or, if not, require an impractical amount of images, like hundreds or thousands of images. Now, that's because we lack the way to correctly constrain the reflectance. We need to devise a compact yet expressive representation of the reflectance of all real-world materials, just like all these 100 samplings of the real-world materials in the MOLD database, so that we can actually reliably estimate them from images, right? And this, of course, sounds like a tough challenge, but you notice that real-world reflectance is not arbitrary. If you think about the reflectance as a high-dimensional vector of input and output directions, it's not like you can have a random vector in this extremely high-dimensional space and call it the reflectance of real-world materials. There's a lot of coherence, like the glossiness. There are some similarities despite the differences in colors, right? So what we really want to do is extract a mold that unifies all these variations while letting us probe into the intrinsic structure that these real-world materials span in the otherwise high-dimensional space. And once we have that, we can actually use that as a constraint to solve these radiometric problems. Okay? So what we did first was to derive a novel reflectance model. So let me give you a really high-level idea without diving into too much of the details. But I really should stress that this is really the key development that leads to all the results in this talk. So as you know, the reflectance can be described by the bidirectional reflectance distribution function that basically just defines it as an abstract function of the ratio of the outgoing radiance in one direction to the incoming radiance from one single point source in one direction. And we'll particularly focus on isotropic BRDFs where the azimuthal dependency is only on the difference. Now, if we think about the BRDF as a distribution of intensity values on the surface of a hemisphere, and just think about putting a material at the base and striking that from the North Pole with the incident light ray, that's good. And if you use the halfway vector parameterization, which simply says that instead of using the incident and outgoing directions, let's use the halfway vector between those two, we will see an intensity distribution on the surface of a hemisphere like this. And if I move the incident light ray slowly down to the grazing angle, it will actually stay at the center and remain almost isotropic. Okay? Now, our key idea is to view each of these 2D slices of the BRDF as a directional statistics distribution. And that's simply to say that let's interpret these intensity values as a probability of seeing light in that particular direction for that particular incident light ray direction. So for that, we derived a novel hemispherical exponential power distribution because the domain is hemispherical, not spherical like in conventional directional statistics. And then mold each of these slices as a mixture of these hemispherical exponential power distributions. Now, the key takeaway message here is that each of these mixture components or reflectance lobes are represented with only 2 parameters, but can express such a wide range of phenomena on the hemispherical distribution. So just to give you an idea, if you take gamma to 0, it becomes flat in an angular space, which means that it's uniform on the hemisphere, which means that it's purely Lambertian. If you take gamma to infinity, it becomes theta h equals 0, which means that the halfway vector is always going to stay at the North Pole, which means that it's a perfect mirror. And we can express anything in between for every single lobe. Okay, so you can imagine how powerful this is. So what we really get out from this is a very expressive parametric reflectance model that can represent all sorts of real-world materials with a small number of parameters. And it's like having an ideal non-orthogonal basis for representing an extremely nonlinear reflectance space. But most important, we can now extract out that linear subspace that these real-world materials span in the otherwise highly nonlinear high-dimensional space. So you can see that even in this 2-dimensional embedding, you get meaningful axes like maybe glossiness on the horizontal axis. And that means that we can now realistically constrain the reflectance estimate that you're going to solve for to be realistic, right? And the DS-BRDF space also directly exhibits a really nice clustering of different materials, which directly lets us recognize the material from the reflectance, okay? So now, on with that reflectance model, let's think about the key problem towards material recognition, which is the long-standing problem of joint estimation of material and illumination of objects with known geometry, but from a single image, okay? And at this point, we'll assume that the illumination is a point source. So this is the conventional physics-based vision approach, but we'll build it up from there, okay? And for now, we'll assume that the material is only one, meaning that we only have to recover one BRDF. Now, we'll think about the probabilistic approach, a formulation, by modeling the image as being generated by 2 random fields, one that encodes the reflectance for each of the pixels, meaning each of the surface points corresponding to each pixel, with the DS-BRDF parameter values. And we'll also have another random field that encodes the illumination in the local coordinate frame, but because we know the geometry, we can always transform the global lighting direction into the local coordinate frame, so that's statistically independent. But the key here is that we can now consider the joint estimation of illumination and reflectance as maximizing this posterior of the factor Markov random field. And now we have a way to incorporate really nice statistical priors on the reflectance, okay? So what we'll do is represent the BRDF with the DS-BRDF parameter values. So if we say, for instance, use 15 eigenfunctions, we'll have 15 coefficients for each of the lobes and colors to recover. And we'll assume a simple Gaussian noise model, but the real key here is that now because we have the DS-BRDF model, we can encode a prior in that space that lets us use a really simple analytical function like a multivariate Gaussian that tightly constrains the span of real-world materials, okay? So here's an example result. For a given single image of this material, we can recover the full BRDF. So this is a sphere rendered with different lighting conditions to show you that we are really recovering the full four-dimensional BRDF just from this limited amount of angular samples that matches this ground truth very well. And you can, of course, re-render this, but also re-render this object from different viewing conditions and lighting directions. Now, that's simple, right? I mean, the results are simple. But let's try to make this much harder by estimating the reflectance of objects that consist of multiple materials just from a single image, okay? Now, this is much harder because now we have to tell which pixel is which material. So we now have to solve this material assignment problem or segmentation problem. And for instance, here you see that this is gold paint, but despite the fact that they look very different in the highlight and outside, we need to be able to tell that it's the same gold paint. Well, the computer has to. And then we have to recover the reflectance from this limited amount of curvature, which means that we have less angular samples. And for that, we take a similar formulation, but instead of just having a single material, we'll stack them up as layers, right? And then we'll have an indicator value associated with each different material, and that indicator value will be responsible for that particular pixel only if it's max across all the layers, okay? And this way we can impose, say for instance, a piecewise constant edge-preserving prior on the indicator values to encourage nice segmentations that also take care of the long-range interactions of even disjoint material regions, while also, of course, using that reflectance prior to estimate the material properties at each single region. So here's a result. Just from this single image, we can recover all the information to re-render that, and all the information means here the indicator values are max values, which is the hard assignment. So this is the hard segmentation of this image or object surface into different regions of materials, and the soft assignments and the corresponding BRDFs that were recovered, okay? Of course, this is not perfect. For instance, you're missing this pink region, but if you think about it, this is almost flat, which means that you only almost have one angular sample of the BRDF, so it's really hard. But there's no reason to just stick to a single image. I'm just being very torturing myself by just using a single image. If you have more images, say for instance, taken under different lighting conditions, of course we can improve these results. Instead of having a single object with different materials, we can have multiple objects of different materials, which might be a little bit more practical scenario. And in that case, we get a segmentation of the scene into objects of different materials. And we can recover the reflectance for each of the materials, which we can see from the relighting. But I believe that this is very compelling, for instance, for robotics, because you can now discern an apple from an orange, despite the fact that the shapes are somewhat similar, okay? Now, let's try to really take this outdoors, because trying to make computer physics-based vision relevant is one of my goals. So instead of trying to estimate the material as reflectance under a point source, let me try to recover it under natural illumination. Now, instead of a point source like this, which was really nice and made things a little bit simpler, we now have this kind of a spherical panorama, which is not even outdoors, but so complex. And that complexity is directly reflected in the image. So that is the complexity that the computer algorithm has to actually take the burden off and decompose that into that natural illumination and the reflectance, right? But if you think about it, the natural illumination shouldn't be something that you completely resent in this context, because we know that it has structure in the distribution of the intensity values and the color values and in the space, right? And that structure is directly reflected in the image, which means that we just have to find a way to model that structure and exploit that in our algorithm. So one thing that you will probably come up like in a second is that, okay, it's a natural illumination, but it's just a natural image, meaning that natural illumination is nothing more than a wide-angle view image. You stick a camera at the center of the object and pan around and take a spherical panorama. That's your illumination, right? Which means that we can take advantage of natural image statistics. And in fact, if we compute the gradient distribution for many spherical panoramas, we find that they do actually have a heavy tail distribution where alpha is around 1.2. So that's directly a really nice statistical prior. But there has to be something else that we can actually exploit. And for that, let's think what the reflectance does. Now, if you have a material that is a perfect mirror, you're just directly getting the natural illumination. If it gets more matte, that reflectance is modulating the natural illumination in local regions, and that is shown to be a bandpass filter in the frequency domain. Now, what does it really mean? That means that if you look at the histogram of the observed image, that is the histogram of the natural illumination modulated by the reflectance. And because the reflectance smears the colors in the local neighborhood of the natural illumination, that means that we'll create new colors in between the original natural illumination colors and thus spread the histogram and thus increase the entropy, which in turn means that we ought to recover the natural illumination to have lower entropy. So there you have a really nice information theoretic prior on the natural illumination together with the statistical prior, and we can combine that with the reflectance prior to solve this hard problem. So just from a single image like this, we can recover the natural illumination surrounding this object and the full BRDF, which of course lets us render this object from any viewing direction, but also even objects that have lower frequency characteristics than this object, we can perfectly predict how it will look like. So there's a really strong reason to explicitly recover the natural image. Now, one thing to remember here is that the reflectance is acting as a bandpass filter, so of course you cannot recover all the high frequencies that were not transmitted by the reflectance, which is why this is patchy, right? But it captures the gist of the scene. The other thing is that we have to also solve the color constancy problem because we can't tell whether the reflectance is green and the illumination is white or vice versa, which we just resolve by saying that, okay, on average, the illumination is gray, but if you're allowed to click on a point, we can easily correct for these color shifts. What's more important is that the shape of the reflectance agrees well. So we took this really outdoors, took images of this, our favorite piggy bank, and we can now recover both the natural illumination and the BRDS. And if you close your eyes to the color shifts, you can see that they are some fairly consistent among the recovered ones for each of the images. And that lets us, of course, re-render. And this is the comparison to the real natural illumination. And you can see that the scene is really recovered from the single image of an object whose material you don't know. Okay? And here's some more examples. And it's quite remarkable that you can tell what the scene is just by taking a picture of an apple. Now, let's think about another important problem. And I'm going to go through this really fast, but I think this might have some interest in the human vision people too, which is about the shape and reflectance estimation from a single image. Okay? So now we are going to assume that the illumination is no, but it's going to be a complex natural illumination. And current computer vision focuses on geometry reconstruction of Lambertian objects. But they're somewhat in denial because we really don't live in stone and paper world, right? So my key point is that we have to jointly estimate these two. So for that, we need to have a way to tame the reflectance, and that we have already developed. So instead of estimating illumination, we now estimate the surface normals, and the key is going to be imposing the right prior on the surface normals together with the reflectance and coming up the right likelihood representation. I won't go into any of the details here, but the basic idea is that because we now have a really expressive parametric model of the reflectance, we can represent the likelihood as a non-parametric distribution like this of a reflectance map, which tells us which point has a much better well-behaved reflectance map that tells us the more likely surface normals. And then it's about propagating that certain information to uncertain regions using geometry priors, like conventional ones using occluding boundary, matching gradients, and imposing some smoothness. Nothing very special here. But the key is that we can combine this with the reflectance prior to solve that joint problem. Now, I noticed that you guys are obsessed about looking at these blobs, so I just will flash some of them. But the key is that we made a lot of synthetic images, like 600 of them, to analyze the combination of different illumination and reflectance that leads to better accuracy of geometry, which I think is a really interesting topic. And say, for instance, you need this kind of a structure in the illumination to get better results, but if it's repetitious like this, that geometry accuracy will go down. But that also is dependent on what kind of reflectance that you have. But let me just show you the real results. Just from a single image taken under known illumination, we can recover the surface normals and integrate them to get the depth. And again, the interesting thing here is that the more signals that you have in the illumination, and if the bandpass filtering of the reflectance matches that very nicely, you get better results in those areas. Whereas if you have these kind of low frequency or high frequency repetitions, you get less accuracy in the results. Here you can see that in the bottom part too. There's not much signal here, which results in less accuracy. We recently extended this to exploit multiple views, like 12 images, not like hundreds. And from these 12 input images and the known illumination, we can recover the full geometry of that object, right? Together with the reflectance. And you can see that we can nicely carve out the mane and the legs of the horse, which you can never get with just, say, for instance, feature-based reconstruction or space carving. Here's another result, and you can see that the ears and the nose of the piggy bank is popping out, and the protrusions of the seashell is coming out nicely. And these are the reflectance estimates. Again, we are kind of purist computer vision scientists, so we really don't want to click on a point to correct for the color shift. So you have these color shifts, but the key is that these agree well across different instances of the illumination. And if you still live in the denial thinking that Lambertian is enough, if you use a Lambertian assumption, you get really erroneous geometry, which is, of course, understandable because the combination of reflectance and illumination and shape leads to explaining that image. So any simplistic assumption in one will lead to erroneous estimates in the other. Okay? Okay. So let me switch gears and talk about the contrasting approach, which is probably going to be somewhat similar to what you talked about just before. And in this discriminative approach, I want to directly classify each pixel into different materials. And this is very different from recent work in describing and recognizing scenes based on their attributes, because we're talking about local recognition. And this is also not texture recognition, per se, because texture is really just one aspect of material appearance. And there are, in fact, 2 papers in the past that tackle discriminative visual material category recognition at the image level, which one of them is what Ted was alluding to. But they heavily rely on object information. And just like he explained, you carve out the occluding boundary of the object and compute features across them and along them, right? But that's almost getting into the object recognition domain. It's not really clear whether you're recognizing the object or the material. What we really want to do is recognize the materials locally so that that information can help us in those high-level image understanding tasks like object recognition. And in fact, those 2 works report very low accuracy when applied locally. So why is that hard? Now, obviously, materials have large interclass appearance variability, right? These objects are all made of plastic, but they have very different looks due to the different instantiations and shapes and colors and environment, right? And even worse, it's really unclear what kind of features we should be looking for to recognize them as plastic, right? Now, if we look at these images, we see that they're all made of plastic, right? And we can somehow tell that because we know that plastic has these inherent properties that exhibited in the visual scene that we can recognize, right? So for instance, plastic is usually smooth, translucent, it has these vivid colors that make them really look artificial. So let's try to express materials based on those common visual traits of materials. So we propose to represent each material as a combination of the probabilistic presence or absence of these visual properties, like shiny. And it can also be these visual properties exhibited by non-visual properties, like tactile ones, like smooth, right? So the hope is that each of these material traits are going to exhibit a more discriminative visual material appearance than the material category itself. So here, the example here is that the koala pixels are fuzzy and the background is organic leaves. So for instance, we want to say fabric can be soft and fuzzy, but not hard or liquid, right? And we want to do this locally. So just to give you a better idea, here are the correctly recognized visual material traits. And I'm saying it's a pixel level, but of course we can't do anything with just an RGB pixel. So we are going to think about local patches centered around each of the pixels. And these are the correctly recognized patches for each of the 13 traits that we predefined, ranging from shiny to organic. And you get a sense that they do encode these visual characteristics of these traits, like shiny often has these highlights passing through, organic has these typical organic color and patterns, right? And of course, these are not mutually orthogonal or exclusive. Metallic is somewhat similar to liquid, and fuzzy is very similar to soft, right? So you get an idea, and we can recognize them fairly well. So how do we do that? As I said, we really don't know what features to look for, so we'll just learn them. So we'll learn them by preparing a sparse convolutional autoencoder and feeding in a lot of local patches and learn the basis as convolutional kernels, which is just about minimizing this error function, which basically says that if you convolve and deconvolve, the reconstruction better be close to the original, and just impose some constraints that avoids it from becoming a delta function, and let's encourage some spatial sparsity. And then you'll get a bunch of bases that represent those local patches. And if you look at the frequency they fire for different visual material traits, like soft, smooth, liquid, and organic, you see that they are trying to encode the characteristic visual properties of these traits, like soft and liquid are checking for these really tiny edges, whereas smooth and organic are looking for bigger edges, okay? So these are certainly very useful, but they're linear. So let's supplement that with the usual gang, the nonlinear features, like histogram of gradients, local binary patterns, and color histograms, and then just do a group-wise feature selection, which just simply amounts to preparing a lot of classifiers with different combinations of features and picking the one that returns the best result, okay? And if you look at how frequent these features are used for different traits, they are somewhat uniform, which really signifies the fact that all of them are important to recognize these material traits. So what we get out from this is a classifier that tells whether a pixel has that particular visual material trait or not in floating values, right? So if we threshold that with 50%, this is the accuracy. And you can see that on average, we get about 80% recognition accuracy, despite the fact that this is not one versus all. This is independent recognition for each of the traits. Now, and one thing to note here is that some of them are more difficult to recognize, like metallic and translucent, but that's understandable because the material itself is just modulating the surrounding scene, so it becomes more about recognizing a scene rather than the material itself because it's just reflecting or refracting. So here's some of the results in the images. So for a single image, we can now compute the 13-band image with the likelihood of each of the traits. And if we threshold that by 50%, these are the pixels that are strongly fuzzy and soft. And as I said, they're not mutually exclusive, so the fur can be both fuzzy and soft, right? And the bare skin is rough and the water is liquid. the house is man-made, the lawn is organic, and the clouds are translucent, right? And this is a pixel level independent recognition, so of course it's noisy, but of course if you'd like, you can impose some spatial constraints using a CRF. Now let's think about using these visual material traits for a little bit higher level image understanding tasks. If you compute the class conditional probabilities of the trait probabilities for each different material category, like fabric or wood, you see that they convey some nice discriminative information about each of the categories. Like plastic is often smooth, rarely rough, and almost always soft, right? So you can interpret that like that. Of course, sometimes it might not make physical sense, like stone is never soft, but it's firing a lot for softness. But porous stone can have a soft-looking appearance. So what we do is compute these histograms for all the categories, for all the visual traits, strip them out as vectors, feed it into a histogram intersection called SVM, and boom, we can do object material recognition based on the traits. And that leads to the state-of-the-art accuracy for local recognition. And this is the key point that I'm trying to advocate, that we should be doing local material recognition. But that's not the only way that you can use the visual material traits. They themselves tell you a lot about the scene. For instance, if you do image segmentation just based on the color, say for instance, just apply normalized cuts to the color, you get a segmentation like this. But now you have this 13-band initial information. You can apply a segmentation to that and nicely carve out the objects based on their materials. Right? And here's some more results. Without and with, like the sea otter or whatever it is. Now, finally, let me show you how we can use this for object detection. In the training data, we have these bounding boxes. So for each of the bounding boxes of a class, we can compute the visual material traits and train a classifier that tells us whether that particular image or bounding box has the visual material traits of that specific object, right? So here I'm showing you the false positives correctly called in green and the true positives correctly preserved in blue. And here, for instance, you can see that the horse detector is firing on sheep, but the visual material traits are telling us, no, that skin is too fluffy to be a horse. So you can call these false positives. And as you can imagine, false positives are really a headache for object detection. So to summarize, I talked about two distinct approaches towards visual material recognition. One was a generative approach, where the key really was to develop the right reflectance model to represent the variability of reflectance, and that lets us really pull out the right prior on the reflectance so that we can solve these radiometric decomposition problems that are really ill-posed. The other one was a discriminative approach where we introduced this notion of visual material traits, I think, which also agrees well to the way that we look at materials and use that for recognizing material categories, but also doing these kind of scene understanding tasks. And really the take-home message that I really wanted to convey was that we really ought to look into ways to exploiting materials in image understanding tasks in computer vision. And that requires solving really severely ill-posed problems, but we can really also devise the really clever way to constrain the important variables. And I hope this will inspire you to research other ways too. And to facilitate your research, we've made available the code and data for most of our research, so I hope you'll visit our webpage and download and start some material recognition work. Thank you very much.
Thank you. Questions?
So, yeah, so in the multi-layer thing that you had in the first half, how did you know, did you give it K, or is that something that's also estimated?
No, that's a good question. We can do the brute force thing of trying different Ks, right, and finding the one that gives us the best statistically normalized error.
Right, so but do you have some kind of information criterion to make sure you're not overfitting? Because you could have a zillion.
Right. like the student t-test.
Right.
Yeah.
Okay.
Does the scale affect the accuracy of the material classification? For example, if in your slide you can segment the penguin very quickly, but if the picture shows a crowd of penguins, then how?
Yeah, that's a very good question, and how the scale affects the how the scale in the data set affects the recognition is an important question that we haven't really answered. And we once tried to actually account for scale by preparing patches of different scales, but it seems like, and this might be obvious to you guys, that scale is really critical. And to recognize a material, it has to be seen at a certain scale. So for that reason, we are only training at the scale the images are given. So yeah, it's a very important question, I think.
Questions?
I was going to ask you a question. So on the last part, the way you were sort of trying to augment object recognition from material recognition, you seem to the way you've done it right now, it seems to add value on the sort of at the back end, you're removing things. But do you think about taking the features that you've derived or the outputs of the classifiers and embedding them as part of a more global sort of feed-forward network in the standard way?
Yeah, certainly. I think that's a really important question. How to combine the object information and the material information in a way that they reinforce each other is a really beautiful question to ask, and we haven't really gotten to that point yet. But this is really to demonstrate the importance of doing local recognition of materials. Otherwise, if you had a material recognition classifier that recognizes based on the object, there's no point of doing this, right?
Questions? I have a question.
How did you select the material traits? So is it arbitrary or some?
So that's another great question, and maybe some of you might have the answer, but in this case, the 13 visual material traits were just simply selected because my graduate students were comfortable labeling them. And that's another really difficult problem, right? How do you describe traits, and how are they, you can, communicate with other people so that you can agree on those? So one direction that we are actually pursuing right now is to discover these traits rather than imposing them, which means do a lot more weekly supervised learning to directly recover the traits from the images.
Is there any optimal area, visual area, or size number of pixels to recover material traits?
I think that also is related to the scale, and also related to how, so if you make it really big, now you're doing object recognition. If you make it really small, you're really throwing out the nice meaty characteristics of the material. So that's I really don't have an answer to what's the optimal pixels.
Okay, I have a question. So you showed nice model of BRDF, but I think the BRDF database from R is limited to some categories. So setting or some very complex object is not included. So how about?
I strongly agree with you, and I think one of the limitations, one of the limitations that really hindering the development of physics-based vision approaches is a lack of data. And the lack of data comes from the fact that it's damn hard to measure, right? Just like Henrik was showing. So one of the things that we might want to try to do is to bootstrap that data by using these 100 materials, dense samples, and our model, and then go out in the wild and get really sparse samples with sparse illumination directions and keep on throwing it in that space. But of course, that has this problem of biasing those estimates. So I don't have a clear answer to that, but that's definitely a big problem.
Okay, any questions? Okay, almost time. So we have third speaker.